All right, let's talk about an element that's so fundamental, it's literally the stuff of life. We're talking about carbon. But not just as some box on the periodic table. No, we're going to see it as this master architect, the one building almost everything in our world, from the atom up.
So, to kick things off, let me ask you a question. What in the world could your breakfast, the hardest rock on the planet, and every single living thing possibly have in common? I mean, they seem like they're from different universes, right? But they all share this one secret, fundamental connection.
Believe it or not, every single one of them, from the simplest piece of toast to the most complex creature.
Is put together piece by piece by the exact same, incredibly versatile building block.
And that element is carbon. It's the silent hero working behind the scenes, building the world around us, and, well, building us too.
So how does it do it? Really? How can one single element be the foundation for millions of different things? We're talking food, clothes, medicine, books, you name it. That's exactly what we're about to dive into.
And here's where things get really interesting. For an element that's so critical for, everything, there's actually not that much of it around. Get this. Carbon makes up a tiny, tiny 0.02% of the Earth's crust and just 0.03% of the atmosphere. That scarcity just makes its job as the architect of everything even more amazing.
Now, to really understand carbon's power, we have to shrink down, way down, to the atomic level. Because down there, carbon has a huge problem it needs to solve before it can build anything at all. And this right here, this is our first major clue. Carbon-based compounds just act differently. You compare them to something like table salt, an ionic compound, and it's night and day. Carbon compounds have low melting points, low boiling points, and they're terrible at conducting electricity. That tells us that the bonds holding them together must be a totally different kind of glue. The pull between the molecules just isn't as strong. The reason for all this, the very heart of carbon's problem, all comes down to this one number: 4. Carbon has exactly 4 valence electrons. Those are the electrons in its outermost shell. And in the world of chemistry, the number one goal is always to have a full, stable outer shell. So what's an atom to do? Could it just grab 4 more electrons to fill up its shell? Nope. Its nucleus, with only 6 protons, just isn't strong enough to hang on to 10 electrons. Okay, fine. What about losing 4 electrons? Well, that's not going to work either. It would take a colossal amount of energy to strip them away. So carbon is basically stuck between a rock and a hard place. But it gets around this problem with a truly brilliant solution. If you can't win by gaining or losing electrons, you share them. And this is where we meet the absolute hero of our story, the covalent bond. It's such a simple but powerful idea. Instead of one atom stealing an electron from another, 2 atoms each put 1 electron into the middle, and they share that pair. It's not a transaction, it's a partnership. And this whole sharing thing is super flexible. You can have 2 hydrogen atoms sharing 1 pair of electrons. That's a single bond. Or 2 oxygen atoms can share 2 pairs, which gives you a double bond. And nitrogen atoms can even share 3 pairs, forming a really strong triple bond. It's an incredibly versatile system. So why does this work so well? Well, the source material puts it perfectly. These shared electrons basically count for both atoms at the same time. By sharing, each atom gets to feel like it has a full outer shell, achieving that super stable state like a noble gas. It is the ultimate win-win. Okay, so carbon forms covalent bonds. Big deal, right? Lots of other elements do that. So what makes carbon the undisputed champion of building things? It all comes down to 2 unique abilities. 2 chemical superpowers. First up is catenation. This is carbon's amazing talent for linking up with other carbon atoms over and over to form these incredibly long, stable chains and even rings. Then you have tetravalency. Because it has those 4 valence electrons we talked about, it can form 4 separate bonds at once. This makes it the ultimate connector, able to branch out and build in all directions. And the secret to catenation is that the carbon-carbon bond itself is just ridiculously strong and stable. Other elements, like silicon, they can form chains too, but those chains are way weaker and more reactive. Carbon's stability is what lets it build the molecular skyscrapers that make up life. So you give carbon these 2 superpowers, catenation and tetravalency, and what does it do? It starts building.
And the sheer variety of structures it can create is, well, it's just staggering. Thanks to catenation, it can form simple, straight chains like the propane you use in a grill. It can get fancy and create branched chains, and it can even loop back on itself to form these really stable rings like cyclohexane. These are like the basic blueprints for millions of different compounds. Now, this leads to a really cool phenomenon called structural isomers. This is where you can have two molecules with the exact same recipe, the same number and type of atoms, but because you arrange those atoms differently, you get two completely different substances with their own unique properties.
And that brings us to the ultimate example of carbon's versatility. It's allotropes. Just look at a diamond and the graphite in a pencil. Both are 100% pure carbon. That's it. But in a diamond, every carbon atom is locked into a rigid 3D grid with 4 others, making it the hardest thing we know. In graphite, each carbon bonds to 3 others, forming these flat sheets that slide right past each other. That's why it's soft, slippery, and can conduct electricity. Same element, 2 completely different worlds, all because of how the bonds are arranged.
And so we come full circle. The answer to that first question we asked? It all comes down to a simple, elegant solution: sharing 4 electrons. That one little act of chemical teamwork unleashes the superpowers of catenation and tetravalency, turning carbon into the master architect of our world. It's just a powerful reminder that from the simplest rules, the most amazing complexity can be born.